We're gonna talk about NP-complete problems again. I'm going to give you a sense of where we're up to and do a quick review. Let's hit it. These star things are the NP-complete problems. A problem is NP-complete if it satisfies two things. It is in NP, means it's someplace in there, and two, every problem in NP reduces to it. A problem is NP-complete if it satisfies those two things. If a problem reduces to your problem, we think of that as meaning that your problem is at least as hard as that problem. So this means that your problem is at least as hard as every problem in NP. Here's a problem out here in NP that happens to be NP-complete. It's called the satisfiability problem. Is it possible that it's also inside this circle? The answer is yes. We don't know whether it really has to be out here. It might be possible that it's in here, but nobody knows. So we don't think it's ever going to be possible to get a problem that's NP-complete inside here, because then all these other hard problems that nobody's ever been able to show are inside here would also end up being in one fell swoop. So showing something as NP-complete is good evidence that it probably isn't inside P. It's probably not polynomial time. Right. We write this like in the following way. If a problem is NP-complete, say M is NP-complete, and you reduce M to some unknown problem called Q, then we know that Q is also NP-complete. Because if M is NP-complete, everything reduces to M. The whole class reduces to M. Everything in here will reduce to here. And then if this reduces to that problem, then everything in here could be reduced to this problem by a sequence of reductions. And all these reductions are polynomial, so if you do one after the other, it's composing two polynomial functions, and you still get a polynomial. So if M is NP-complete and you reduce it to Q, Q is NP-complete, as long as Q is someplace in the class NP. So you got an unknown problem. You want to show that it's hard. You take a problem that you already know is NP-complete and you reduce it to your problem. Okay? If M reduces to Q, I'm going to write this down. These are the two things, the two ways you use reduction. Way number one, M is hard implies Q is hard. That's how we typically use it at this point in the course. We take things that we know are hard, that we know are NP-complete, and we reduce them to other things, and that implies that those other things are also hard. All right. What if you did it the other way? What if you did this? And you knew that M was hard, and you reduced Q to M. What does that tell you about Q? Doesn't tell you much. It tells you that Q is easier than a really hard problem. How much easier?
We don't know.
We don't know. Could be a lot easier. Could be constant time, could be linear, could be exponential, we don't know. So you would never reduce an unknown to an NP-complete problem and expect to get anything interesting. Doesn't work that way. You don't reduce things to hard things if you want to show anything about them. So what can you do? You reduce hard things to your unknown things. That shows they're hard. What else can you do? The other way to do it. Let's say you reduced M to Q and you knew that Q was easy. We did an example of that yesterday. We reduced two satisfiability to strong components, strongly connected components. We know how to solve strongly connected components with a depth first search. So we know this problem is easy. We reduce this problem to it. So what do you know about this problem now? It's also easy. Okay? So if Q is easy, that implies M is easy. These are the two ways you can use reductions. You can use it in either direction as long as you make the right conclusion. Other questions about that? This is a review meant to give you some context. Everybody okay? It's very common that people try to show something as NP-complete and accidentally do the reduction in the opposite way. And we're going to do an example of this in just a minute, because you should see the examples that don't work. It'll make you appreciate the examples that do work better. Okay, so are there any problems that are NP complete that we know for sure are not inside P? No, there's not. They might all be inside P for all we know. But we don't think they are, because if one is, then the rest of them are. They're all linked together. They all go together. If one steps in, it's like a mass suicide. If one steps in, they all go. And we don't think everybody's going to go, because everybody's been working on these people to make them sane for hundreds of years. Nobody's been able to do it. They're not all going to suddenly commit suicide at once. Take it or leave it. Are there any problems in NP that are not NP complete? There are tons. All the things inside this middle bullseye are in NP. They're also in P. I mean, they're inside the bigger bullseye. None of these inside here are NP complete. It's impossible for these to be NP complete. If they were, then these two things would collapse. Not impossible, but unlikely. So all the problems in the middle certainly can't be NP complete. But are there any problems that we don't know are in the middle, that are out here, but are not NP complete? We'll mark those maybe with a dot instead of a star. A problem that is not inside P, or we think is not inside P, that it's out here in NP, but isn't NP complete. Is the world just made up out of things that are P and NP complete, or are there things in the middle? Everyone understand that question? So the answer is we don't know. There's a lot people don't know about this. Nobody knows the P equals NP problem. Nobody knows the answer to it. It's a big open question. Nobody knows whether there's a problem in here which can possibly not be in P, but also not possibly be NP complete. Nobody knows whether there's any such intermediate step. But there's a good candidate for something like this. A good candidate would be a problem that people have worked on for 100 years and never ever gotten a polynomial time algorithm for, but have been working on for 30 years and can't find any reduction to it. Any problem like that is a good candidate for a problem that is neither NP nor NP complete. So there's a great example of this, and it's at the heart of all the cryptography stuff, and it's factoring. The best algorithms people have for factoring are exponential in the size of the number, in the number of digits. If you give me a number with a certain number of digits, the best factoring algorithm I can do is exponential in that number of digits. The normal thing you do of just going up to the square root takes 2 to the square root of n steps, where n is the number of bits. So we don't have any good polynomial time algorithm for this, and that's why your credit card can be sent over the net, because nobody knows how to factor very, very large numbers into its primes. But nobody's been able to show that there's a reduction from any NP complete problem to this. In other words, this is not known to be NP complete. So it's possible that there is no reduction from all of NP to this problem. It's possible this problem is not as hard as all the problems in NP, but it's still not in polynomial time. It's possible that that's one of them. If we could really identify this, it would answer a lot of questions, including help us answer the P equal NP question. So this is almost as hard of a question as the P equal NP question, whether such a problem exists. And these kind of questions are really part of a topic called computational complexity, which gets a little bit away from algorithms. It's more in the theory of computation arena, but it's a very, very interesting part of computer science where we talk about what we know about the structure of what computers can do in time and space. All right, questions about this so far? This is all big picture. All right, next. I was talking to Kevin the other day about one of the problems on the homework in problem set 4, I think. There's an optional problem in problem set 4 that gives you this information. You're given a bunch of segments. Bunch of line segments. And the question is, give me the largest collection of these line segments such that none of them intersect with each other. The largest independent collection of line segments. Everyone understand that question? How do you do something like that? Well, you might remember from the geometry stuff we talked about that you can check whether any 2 line segments intersect fairly quickly. That's not a hard issue. But figuring out the largest collection where none of them intersect at least brute force requires considering every subset of these segments. And there's 2 to the n subsets of these segments. And checking each one to see the biggest where there's no intersections would take at least 2 to the n time. Maybe there's a more clever way to do it. So I gave you this problem because I think this is a really good problem where you wouldn't be able to find the answer real quick in the book or even on the net so easily. And it just isn't clear whether there's a polynomial time algorithm or whether you can make a reduction from an NP-complete problem to show that it's NP-complete. And a lot of problems are like this in real life when you first get them. You don't really know if you can do it or whether it's hard. And you have to thread the needle. And you try both directions. You try a reduction. You try really hard. You try for 3 days. And you try and try and try. And every reduction you do doesn't seem to work. The harder you try and don't get a good reduction, the more likely it is that there's a polynomial time algorithm. So it's a good psychological thing. Instead of keep trying and trying and trying, getting failure, the bigger your failure, the more likely your success will be on the other side. So you go try the other thing and you work on your polynomial time algorithm. And you work on that for a couple weeks. And you don't get anywhere. Well, then you go back. See, maybe I missed something. And you go back and forth this way. Well, it could happen that you'd spend many, many years and not come up with any conclusion. Neither finding a polynomial time algorithm nor finding a reduction. But very often, and this is a subtle point and a little bit kind of intuitive and not so rigorous, but very often your failure in one side of this process gives you a clue as to success on the other side. Sometimes the inability to come up with a reduction gives you a clue as to what algorithm might work, and sometimes your inability to come up with a polynomial time algorithm gives you a clue connecting this to a problem which is also very hard. So you can't really appreciate this until you do it yourself, but it is a very, very nice way of doing computer science and math to have these 2 things interact with one another. All right, so I haven't yet confirmed the answer to this question. I have a colleague who told me that he thinks it's NP-complete and he's going to check for me. So I don't know the answer. So someone knows. I think this is a known answer, but we don't know. So here's an attempt to try to connect this with something well, not exactly that we've thought about. Kevin connected it to something we have talked about, but I'm going to connect it to something else. There's a problem in graph theory called the independent set problem. And it's a famous NP-complete problem. It's an easy problem to describe. I'll give you a graph like this. And I want to know the largest set of nodes in this graph, none of which connect to one another. It's a lot like this problem, except it's nodes instead of line segments. So let's look at this. What's the largest collection of nodes that don't connect to one another in this graph? You can certainly get 2. Can you get 3? Can you get 3? I'll circle 2 that you can get. You can get these 2. They don't connect to one another. Can you get any 3? You can just brute force check. I don't think you can get 3. So the answer here, the maximum independent set for this graph is 2. It's an NP-complete problem, finding the maximum independent set. These problems seem really very much related, right? So your gut instinct is going to be, okay, well this sounds so much like this, and I'm just going to make a reduction, and I'm going to show it's NP-complete, and I'm going to be done in a second. And here's what I'm going to do. I'm going to take this, I'm going to make every segment here a node. So I have 1, 2, 3, 4, 5 nodes, right? Let me label them. A, B, C, D, E. A, B, C, D, E. And now, if they intersect, I'll make an edge. So A to B gives me this edge. And let's say A to C intersects there. There's an edge. A intersects with D and E. Any other edges I need to add? D and E. Is that it? 1, 2, 3, 4 intersections. 1, 2, 3, 4, 5 intersections, 5 edges. Good. This is it. And now, if I want to solve this problem, I can just solve the independent set on this problem. The answers will be the same. The maximum number of independent nodes here will be the maximum number of mutually non-intersecting line segments here. Right? If these things don't connect, it means these 2 segments don't intersect. So what's the answer here? What's the biggest? What three?
B, C, D, or B, C, E.
B, C, E. So there's three. And that would correspond to these edges, B, C, E. And they don't intersect. And that's the biggest collection of segments that don't intersect. Corresponds to the biggest collection of nodes that don't connect. So what have I done in this whole discussion? What have I reduced to what? Let's call this problem independent set, and we'll call this problem segment intersection.
You've taken the opposite way. Yeah, you did.
Yeah, it depends what you mean by opposite, but I have reduced segment intersection to independent set. I have shown how to take an example of segment intersection and turn it into an instance of independent set. So that if you could solve independent set, then you could solve segment intersection. This is a very nice thing to notice, and it's a good practice with reductions, but it doesn't help me at all know the complexity of segment intersection. It's just showing me that if I could solve independent set, then I could solve segment intersection. An independent set is very, very hard. But that doesn't mean that segment intersection is very hard. It just means that segment intersection would be hard if I did it this way. But maybe there's a better way to do segment intersection. Maybe I can avoid thinking of it like independent set. I made a connection as something that I recognized, but that thing I recognized was hard. Maybe I can make a better connection between this and something else to come up with a polynomial time algorithm. Maybe I can't. Is it the graph that makes this hard? Maybe the segments are a little easier to deal with? So Todd asked me a question yesterday about the bidirectionality of a reduction. We just made a reduction from SI to IS. And remember, the condition that has to be true is that this instance needs to be solvable exactly when the original instance needs to be solvable. This is solvable when this is solvable. They have to be yes, yes, no, no. So it seems bidirectional. But that bidirectionality is only the condition on the actual instance that I've reduced. It does not imply that if I have a reduction from here to here, then I will have a reduction in the opposite direction. In fact, let's try to do a reduction in the opposite direction. Somebody gives me a graph. I want to turn it into segments. That's much harder. Somehow I have to come up with segments that represent these nodes that cross each other exactly the way these nodes connect to each other. How do I do that in general? It's really hard. You can think about it and maybe come up with some methods. But if your method ends up doing exponential work, then that's no good. If you're going to work hard to come up with segments that intersect the way this graph intersects, so hard that it takes exponential time, then your reduction isn't helpful because all the work you did in converting independent set into this problem was in the reduction, and it took exponential time. So solving this quickly isn't going to help you solve this quickly. And the fact that it takes you exponential time in doing that reduction is actually good news. If you try really hard to make a reduction from independent set to segment intersection, and you try really hard, you try it for 2 months, and every single time you try, it seems that you always have to use exponential time. What does that tell you? That tells you that this hard problem can't be converted into this hard problem without actually basically solving this problem, without basically doing exponential work. It means that there's a darn good chance you can just solve this problem straight up. Because if you could get here in polynomial time, then that problem is not likely going to be easy. So here's a very nice example of a reduction that goes in one direction, does not easily go back in the other direction, but the direction that we thought of, unfortunately, doesn't help us. Nevertheless, thinking along these lines is just the right way to go. And it will give you a much, much better understanding of what's really going on here. All right, questions? Okay, good. You think so? You want to wait till you see some more details? Just good. Just no good. Half a thumb. All right. Now we're going to get into details, and I'm going to remind you of all the reductions that we've shown so far by making arrows going down to show that this has reduced to something else. So what have we shown so far? Satisfiability reduces to what? To 3 satisfiability. Yesterday in recitation, Mark showed that 3 satisfiability reduces to a problem called not all equal 3 satisfiability. And then he showed that not all equal 3 satisfiability reduced to a problem called simple max cut. Remember I told you about this problem? You have a graph, you want to split it into 2 parts. You want to get the maximum number of edges between the 2 parts. It turns out it's not so easy to make a reduction directly from here to here, but if you have this intermediate problem, the connection between these two is more apparent. This is very common in making reductions. Sometimes you make reductions to weird, bizarre, twisted problems like not all equal 3 sat, just because it gives you a very comfortable intermediate step to get to something that's a real problem that seems a little more like it. And there's a lot of variations of 3 sat. I think there was a paper by Schaefer. I think so. I don't hope it's by him. And it's basically a paper describing all the different variations of 3 sat that stay NP complete and all the different variations that are polynomial time. That's just what you would do if you were doing research on that. You would try every possibility and see if you could come up with some general rule when it's NP complete, when it's not. Summarizing all of it. What else have we shown? What other reductions have we shown? We did 3 sat to colorability. I think we did the opposite way. We did 3 colorability. Oh, you're right. We did 3 colorability reduces to sat. Now that's no surprise, because we happen to know that everything reduces to sat. We did this just for me to try to convince you that it's relatively easy to take any problem and convert it to Boolean problem. And this is a particular example, one of the infinite number of examples that already reduce to sat via Cook's theorem.
Sat reduced to Minesweeper. Yeah.
Sat reduces to Minesweeper. Anything else? We did do another one. It just doesn't fit it on this diagram. We showed that 2 sat reduces to strongly connected components. This is hard. Going down the branches gets to harder and harder problems. This is unknown. Heading here heads to an easy problem. So going this way gets to easier problems. Going this way gets to harder problems, because it starts from a hard one, and the bottom of this is an easy one. Right? That's what I was saying before. You can use it both directions depending on where we go. If we can now reduce something to 2 sat, we'd show that that problem was easy. So this is a nice result, the 2 sat being here and the 3 sat being here. We've really narrowed that down. We know exactly what's easy, what's hard in that problem. And if you want to be very, very mystical, and please don't be too much in mathematics, but there's a lot of examples where 2 is easy and 3 is hard. Not the least of which is Fermat's last theorem. Right? So there's just tons of examples like that. 2, easy. 3, hard. This problem here is simple max cut. I mentioned many times that if this is a planar graph, the problem's easy. Mark did a reduction yesterday from here to here. Remember the kind of graph he came up with? Graph that looked a little like this. Triangles down here. Edges up here. If you didn't see the details or didn't understand them, don't worry. We're just, what does the graph look like? Triangles down here, edges up here, and then edges connecting each of the triangle nodes to something up there. Something like that. Graphs that look like this. What do you think about graphs like this? If I think about them, can I guarantee that given any formula, a graph like this is going to be planar? Probably not. In fact, I can come up with some pretty easy counterexamples. That formulas which create graphs which are definitely not planar. And you would expect this. There's no way this reduction is going to end up with a graph that's planar all the time. If it did, that means the problem is NP complete even for planar graphs. And we know that the problem is in polynomial time for planar graphs. So there is nobody in the world who is likely to come up with a reduction for simple max cut that always results in a planar graph. If they did, they would show that P equals NP. Everyone understand that? When you do reductions, the kind of instances you come up with tell you something about the restrictions to the problem that you're dealing with. If I could come up with a reduction from here to here and have this graph always have a particular structure, that means the problem is hard even for graphs with that kind of structure. In this example, I can't guarantee a planar structure on this graph, and that's a good thing because if I could already solve that problem. So I don't expect to be able to get that kind of structure. But there is a structure on this graph that you could almost get. There's kind of a degree restriction on these bottom ones. You can only have at most 3 edges coming out of each of these nodes. And each of these nodes is kind of restricted. It depends how many variables appear in different clauses. Like if there's an x in all the different clauses down here, there might be a lot of edges to there. But it turns out we can get rid of this degree restriction and fix it. And simple max cut is hard even if every single degree is 3. Even if it's just 3 edges coming out of every node. So there are some restrictions we can hang on to and the problem's still hard, and some that we can't hang on to, and that implies that we should look for a polynomial time algorithm. Here's an easy version. Simple max cut on trees. Is it easy or hard?
Easy.
What do you do? How do you cut it to get all the edges? Can you get all the edges in a tree?
You can get half of them. No, you could get all. You just have a cut.
Depends if it's a bushy tree or not.
Here's a tree. We want to divide this tree into 2 sets of nodes and get the maximum number of edges in between. Is it an easy problem or a hard problem? Everybody's got a different idea. Okay, I'll label them. A, B, C, D, E, F, G, H, I, J. I'll put A on one side. What should go on the other side? All the nodes that connect to A should go on the other side, so I get the edges going in between. Let's see if I can get all of them. C and E go on the other side. Now, D, F, and G will go on this side. H, I, and J will go on the other side. So now every single edge in this graph goes between these 2 sides. Everybody see that? All I did was make sure that happens. I put the first ball that I started with here. I put all the strings connected to it on the other side. I put all the strings connected to those balls on the other side. How do I know that I'm not going to leave out any edges? Because it's a tree and there's no cycles that could possibly end up going back and forth between these nodes. So not only is it easy, it's trivial. The answer is, here's how you write a program to solve simple max cut in a tree. Return yes, no matter what you ask for. No matter what k the person says, check if it's no bigger than the number of nodes, and if it isn't, say yes. As long as you're not asking for more edges than there are nodes, I can do it. It's a one-line problem for a decision problem. So you should be skeptical. I could easily come up with a problem that I'm going to make you feel is easy, but actually is hard. So be skeptical. But don't be afraid to look at a problem and say, hey, I think I might be able to do that, or I think I might not. You should be very skeptical if I come up with a reduction of anything to simple max cut that always ends up with a tree. It's not going to happen. It's too easy a problem to come up with. All right. Next example. As you know, the partition problem is NP complete. You should also know, based on the problem set you're working on, that the partition problem can be solved in polynomial time if you have very small numbers. Because if you only have, say, numbers 1 and 2, then if you have n different numbers, and the biggest one is 1 or 2, then what's the sum of them all? At the most, the sum of all those numbers is going to be, at the most, 2 times n. You have n numbers, the biggest one is 2. The sum of them all is 2 times n. So if you want to do the partition problem, you take that 2 times n, you cut it in half, you get n, and you make your table, n different numbers, n different capacities. So the partition problem with n numbers, each number 1 or 2, can be solved in order n squared times. And if you fix the size of the numbers, the partition problem can be done quickly by dynamic programming techniques. And you wrote, or you're writing, algorithms to do that. What makes the problem hard is that these numbers can get very large. They can be as big as 2 to the n in size, in which case our algorithm won't run in n times n. It'll run in n times 2 to the n. You'll have n numbers for your rows and 2 to the n numbers for your capacities. That's too slow. So Todd asked me this question yesterday. It's a very good question. What if I don't want to partition the problem into 2 equal halves? I'm giving you a bunch of numbers and I want them into 3 equal thirds. Everyone understand the difference? All right. So your first gut instinct would be, well, I'll go modify my dynamic programming algorithm so it'll handle 3/3. And you work on that for a long time. And you think and you think. And after a long time you realize, oh, it's not easy to modify. And every time I try to modify it, it seems to take a lot of work, a lot of exponential effort. So it turns out, save you the trouble, that the partition problem in thirds, the third partition problem where you want 3 equal parts, that this problem is NP complete even when the numbers are small, even if the numbers are 1 and 2. The reduction to this problem comes up with teeny, teeny numbers. The reduction to the half partition problem is only possible with very large numbers. You can only make the reduction and come up with large numbers. So when you do the reduction to the third partition problem, the reduction ends up with small numbers. That means the problem is hard even if you have edges of just sizes 1 or 2. The problem is still hard. This is NP complete even for small numbers. Problems with numbers as their input, where the size of the number matters and they remain NP complete even when the numbers are small, they're called NP complete in the strong sense. They're called strong NP complete problems. It means don't bother looking for dynamic programming solutions, where you range from 1 up to the highest number. They're just not going to work. So it's worth knowing this, so you don't spend a lot of time trying to solve that problem. All right. Well, this has all been, everything up till now is to try to give you context. It's all been somewhat review, somewhat filling in different pictures, somewhat sharing conversations I've had with individual students, with everybody that I thought are worth sharing. Now we're going to go back to this big picture of what we've done so far and expand it out a little more. We're going to start by doing a reduction from the Hamiltonian circuit problem to the traveling salesman problem. We're then going to take 3-sat and turn it into a problem called vertex cover. And then we'll take vertex cover and turn it into Hamiltonian circuit. Then we'll take vertex cover and let it go to dominating set. Dominating set. Vertex cover. Whoosh! This tree grows like crazy. We won't finish this today. We'll probably do this next time. We probably will be able to do this one, and this one. This reduction takes a little bit of time to explain, and if you're tired, it won't sink in. But these 3 I think you'll be able to get. And that's what we'll try to do between now and the end of the lecture. I picked these 3 today on purpose for the following reason. They represent, in some sense, 3 different styles of reductions, which I will call easy, medium, and hard. Gary and Johnson have better descriptions of these, but the bottom line is that it's just a subjective description. And what they really mean is easy, medium, and hard. This one's easy. This one's medium. And this one's hard. So we're going to start with the easy one, and then work our way through the others. Getting good at reductions takes, number 1, lots of experience trying it. Number 2, lots of expertise and familiarity with the particular problems that you are reducing to. If you get a new problem and you're not familiar with it, you're not likely to notice the features of it that connect to other problems. You have to be kind of a little mini expert in a lot of different areas. It's not easy to do this reduction that Mark did yesterday from 3-set to not all equal 3-set unless you're pretty comfortable with Boolean formulas. If you're not, it's just going to be a lecture in the clouds. I'm going to do a reduction, not today, but maybe next time, another variation of this called 1 in 3-set. When I'm going to show this to you, or when I'm going to show you any of these reductions, you're going to get the sense of, or you should ask yourself, well, how do you figure these things out? And there is no rule of how you figure them out. It is very, very, very dependent on the skill of the individual and on their familiarity with the problem and on how many of them they've done before. And you can wander around in a dark room for a long time not seeing what you're looking for. What you should expect of yourselves is when somebody shows you a reduction, you should be able to appreciate why it works. You might not be able to appreciate where it came from. It would be very nice if every paper somebody published with a reduction came with a short little anecdotal section about what I tried that didn't work and how I actually found the thing that worked. Because that's what's going to make you good at doing reductions, is working with somebody and seeing when it doesn't work and watching an expert quickly cut off the bad tries and go to the good tries. But you won't find that in any text or any book because it's just a waste of paper as far as the journal is concerned. Right? But it is something that is useful. So maybe we can try to talk about it when I do this in a different day. All right, so now, this, and then this. Questions so far? Okay. Reduction number 1. Hamiltonian circuit reduces to the traveling salesman problem. We need to review what these problems are. Hamiltonian circuit, who remembers what that is? Who remembers? Doug, who remembers?
Whether you can connect through all the nodes on a circuit without passing one twice.
Good. Given a graph, whether you can go from any node on the graph, hit all the other nodes exactly once, not more than once, exactly once, not less than once, and then end up where you started. Good. That's NP complete. I gave you an example of this in discrete math that isn't obvious. Here's always a nice example to look for a Hamiltonian circuit. If you just write down a random graph on the board, it almost seems obvious that whether it has a Hamiltonian circuit or not. And you can't appreciate the difficulty of the problem until somebody comes up with an example that really makes you think for a minute. Does that have a Hamiltonian circuit or not? Well, you can think for a minute. Or just remember from 3 months ago. Traveling salesman problem. Traveling salesman problem is perhaps the most famous NP-complete problem there is. It shows up all the time in the newspapers. In fact, I Xeroxed an article for you that showed up in the New York Times about 3 or 4 years ago that is all about traveling salesman problems really hard, but we still bang at it anyway and try to solve as big of a instance as we can. And I forgot to bring in the copies, but they're sitting there, and I'll give them to you after lecture today. So it's a fun article to read. The traveling salesman problem says you've got a whole bunch of cities, they're connected, and you measure the miles between the cities. So it's a graph with weighted edges. Okay? And you want to start at a particular city, go to visit every other city exactly once. You don't want to backtrack. You're an anal, compulsive salesman. You will not go back to a city once you've been in there. You will not miss a city. So you go through every single city, and you want to get back to where you started, and you have to do it in the minimum number of miles. Okay? You're very frugal. You don't want to spend any extra gas. Everyone understand that question?
Is the graph complete? Are all of the edges, or all the...
In practice, we usually imagine that it's just a bunch of cities on a piece of paper, and you can get from any, like you can take a plane from one to another. But in formal ways of describing the problem, it's just a graph. And there don't have to be edges between every 2 nodes. The problem becomes more difficult and generally hard when you do allow plane trips between every 2 nodes. But right now we're just saying it's any graph. There doesn't have to be connections between every 2.
It's more difficult if you can get to any node from any node?
Yeah.
Surprising.
Yeah. Because then it's this minimum part that makes it hard. There's a lot of actual Hamiltonian circuits, but you got to find the one that's smallest, and that makes it hard. That's an engineering thing because, well, Yeah. So, which of these problems do you think is harder? Just gut instinct. I mean, gee, right? I mean, here's a graph. Can you start here and get back to where you started? And here's another problem. Same thing, but do it with the smallest distance. Duh, it's got to be harder to figure out whether I can get back to where I started with a minimum distance than just to figure out whether I can get back to where I started. I mean, it's just a harder problem. It's just the same exact problem, but more. In fact, if you think about it, the Hamiltonian circuit problem is really a very special case of the traveling salesman problem. The Hamiltonian circuit problem is a traveling salesman problem where there's 1 mile between every single pair of cities, and I want to know, can I start in this city and go back to where I started and do it in less than n miles? That makes me go through every single node once. So what's the reduction? Here's the reduction to show you go from here to here. It's an easy reduction. It's called a restriction. This is a restriction of this. This is a generality of this. Anytime you have a problem which is a general case of another problem, then the reduction is almost automatic. Here's the reduction. You're given a graph. How do you turn it to a traveling salesman problem? Traveling salesman problem needs a graph and a bound to try to get better than that bound. So here's what we'll do. We'll call this graph, given G, we have to construct the graph for this, which we'll call G prime, and we have to construct B, which is the integer that we're going to try to beat the traveling salesman problem tour by. So the size we're going to beat it by is going to be how much? N, the number of nodes. And the graph is going to be the same as the graph we started, with edge weights all equal 1. That's the reduction. Take the graph, don't do squat with it except put weights on it of size 1, and then try to get a traveling salesman tour of size n. Can you do it of n or less? Well, you'll never be able to do it in less than n, but you can do it in n by going through every node exactly once. If you can solve this, you've solved this. They're the same problem. This is a general version of this problem. This is a restricted version of this problem. The reduction is nothing more than specifying the details of the general version that make this the special case. Now, let me stop there. This is an easy reduction. So if it seems a little challenging, think about it and see if you can figure out what is confusing, and I'll stop for questions now, and then I'll move on. Questions about this reduction?
Is traveling
Michael?
salesman about how many, what's the, can you do this many cities?
No. The minimum weight through all the cities. You have to get through all the cities.
Okay, what's B?
So B is the weight that you're trying to beat. Anytime we have a minimum problem in a decision situation, we have to add in the number that we're trying to beat and say, can you get less than or equal to that? So if we can get less than or equal to n in this graph, then we've got a Hamiltonian circuit. And if we have a Hamiltonian circuit, we can get less or equal to n in this graph. Because every node we go through costs 1 mile. You get it? Thinking about it still. Okay. The reduction's easy, but this is not obvious. So if it's not screaming at you yet, look at it again and again. It's just a reduction that doesn't take much work. It's not trivial and it's not obvious. It's just easy to write the reduction. Yes?
The traveling salesman doesn't have B as part of it. That's just
No, it does. The traveling salesman problem has yes. Let's review.
It's just a minimum, though. What?
Yes, but anytime you have a problem that asks for a minimum, the way we describe it is a decision problem. And here's how we'll describe the traveling salesman problem. I give you a graph. I give you a number. Can you get through all the nodes in this graph and have the sum of all those weights be less than or equal to that number? That's how we describe minimum problems. So I describe that by saying the number here that we're trying to get.
It's that decision thing.
Right. It's that decision conversion that makes this a little tricky. This is a subtle point. I mean, I'm kind of glossing over it. It's a minor subtle point, but it does work just as easily as I wrote it. Other questions? It's a good question, Neil. All right, let's let this reduction go then and go to a different reduction. It doesn't build on this at all. Now we know there's a connection from Hamiltonian circuit to traveling salesman problem. And now we're going to go back to the vertex cover problem and connect it to a problem called dominating set. I need to tell you what these two problems are. And then at the end of the day, we'll connect 3 set up to vertex cover, and we'll complete this tree, except for this little branch here, which we'll do some other time. Vertex cover is a minimum problem. I give you a graph. I give you a number, like 3. And I ask you, can I cover this graph with 3 or fewer vertices? Cover. Not colorability, cover. I haven't said what cover means. If you're thinking, what the heck does he mean by cover? You should be saying that. What do I mean by cover? Here's what I mean by cover. Here's 1, here's 2, here's 3. Every node that I mark or I cover this is a town wiped out by a flood. These are intersections. You rebuild ice cream shops and all the intersections so that everybody on any street can get to an ice cream shop on one end of the street or the other. Then I've covered the town with ice cream shops. I want every edge in this graph to be connected to something in the cover. That's called a cover. Is this covering the town?
Yes.
Yes or no?
Yes.
All right, smarty pants. If it's no, then
I
tell
see
me.
the edges. You're right.
Tell me.
She's
Where's
right.
that edge?
Right. People who live on this block, right. So Chris doesn't like ice cream so much, because if he was living on this block, he seems not to be upset that there's no ice cream shop on the corner of either one. This 3 vertex set is not a cover of the graph because it doesn't handle this edge. Can we cover this graph with 3 nodes? Yes or no? Everyone understand what a vertex cover is now? This problem is NP complete, by the way. It's hard. Finding the minimum vertex cover is hard.
Yeah, you can.
How do you do it? Joe, you got away?
The 2 you just had, and then 1 on the more. No, that one over. That one, go up. That one, and there's 1 all the way down the bottom. Yeah.
No, got the lower diagonal.
This one's still missing. And you get to live there. No ice cream for you. That's a good try. Can we get them all with 3, or do we need 4? Everybody get the problem? I don't really care about the answer. I care that you understand the problem. Everyone understand the problem? Questions? All right. This problem is hard. We're going to do, you know what I'm going to do? Yeah, well, you'll see. You'll see. There's another problem called edge cover. This is a problem where I'm picking, instead of picking nodes, I'm picking edges. And I want every node to be covered by one of the edges. That's kind of the dual of this problem. So let's look at this graph. What's an edge cover for this graph? I can pick this edge, this edge, this edge. Is that an edge cover? I still need one down here. These problems look awful similar, right? One's covering nodes and hoping that the edges get covered. One's covering edges and hoping that the nodes get covered. This problem, recognize this problem? Anybody remember this problem? This problem is the marriage problem. It's getting as many marriages as we can finished where the edges represent people that are willing to be married. This is called the maximum matching problem. The edge cover problem is a completely famous polynomial time problem. It's a graph problem. It's related to maximum matching, which is in turn related to the max flow problem. There's an n-cubed algorithm for this and some better ones if you look in the research. So this is an easy problem. That's a hard problem. They seem similar. If you thought they were similar, it just reflects just how little we really understand about both problems. They're really not similar at all. This is easy. This is hard. Keep that in mind. There's another problem that looks a little like vertex cover. You look back in your notes, first day of class. That's also easy, even though vertex cover is hard. What I'm going to talk about now is another problem that looks just like vertex cover, but it really is hard, called dominating set. In the dominating set problem, you're still covering up nodes. Okay? You're still putting ice cream shops on the corners. You're not picking edges like edge cover. You're still covering nodes, but instead of trying to have all the edges connected to your nodes that you've covered, you're just trying to get all the nodes connected to the nodes that you've covered. So this is nodes cover edges. And this is nodes cover nodes. I hated this name vertex cover when I first saw this problem because I always thought of it as you're covering the vertices. But it's really you're choosing vertices to cover edges. So I think these problems are actually worded backwards. I think vertex cover should be edge cover and edge cover should be vertex cover. And you don't need to know about that. But you should just know, when everybody else in the world talks about vertex cover, they mean nodes covering edges, vertexes covering edges, vertices covering edges. When they say dominating set, they mean nodes covering nodes. What's an example? What's a dominating set of this graph? Let's choose this. This covers boom, 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 boom. Right? So what's left to do? One of these two in the corner. So generally speaking, it's easier to find a dominating set than a vertex cover in the sense that you need fewer vertices to get a dominating set than you need to get a vertex cover. It might not be easier to find how many fewer, but one covers edges, one covers nodes. You can cover edges a lot more easily than you can cover nodes. You can get more for your money.
You mean the other way around?
Yes, I do. I mean, you can cover... Get more for your money in this problem. All right. We're going to show that this problem is almost the same as this problem. And your gut instinct here, now you should be getting it, is that picking vertices to cover a graph is hard. Picking edges to cover a graph is easy. It doesn't matter how you're covering them. Picking vertices to cover a graph is going to be hard. Whether you're trying to cover the edges or whether you're trying to cover the nodes, it's the choice of the vertices that makes the problem hard. And when you're choosing edges to cover a graph, like edge cover, that's easy. So how do we do this reduction? Let's write down what we're going to try to do and run through it. Vertex cover reduces to dominating set. With most reductions, I'm going to show it to you with an example and try to describe to you what the reduction really does in general. So let's do that. A, B, C, D, E, F, G, H. And say we're trying to get a vertex cover here of 5. Okay, I've got a big graph. I want to know, does it have a vertex cover of 5 or less? I'm not trying to solve this problem. I'm trying to show you how to convert this problem into a dominating set problem. When you do a reduction, if your gut instinct is to try to look at this and solve it, then you're doing the wrong thing. You should be trying to make a connection between your problem and another problem, which most certainly should not involve solving it. Let's try to make a transfer from what makes this a vertex cover to what makes some other thing a dominating set. Now, we don't know what that other thing is, but we can make it up. We can make up any other graph we want. we'd like to have the graph that we make up have the same kind of dominating set structure as this has a vertex cover structure. And this is not obvious. But it's kind of a medium level reduction. When I show it to you, I think it will make sense. Well, here's the obvious thing to try. Let's not change the graph at all. Let's just copy it. Okay, I use the same graph. I'm hoping to God I don't have to do anything. And I say, this has a dominating set of size 5, if and only if this has a vertex cover of size 5. Is that true? No. There's going to be plenty of dominating sets here that don't correspond to vertex covers here, and vice versa.
Can you do a dominating set with a directed graph?
I guess you could, but it's defined as from undirected graphs. You could define it for directed graphs.
Add a node in between each of the nodes.
You mean add a node on each edge? Let's try that. You better give me a reason. So Jeff says, I'm just going to chuck in a bunch of these nodes like this. Everybody sees what he says? Why does that seem like a good idea? Why does his gut instinct seem reasonable? I'm not saying it works, but it's certainly along the right lines.
Because it would make us have to pay attention to the edges coming out of each of these nodes, because we have to cover them.
Right, let's say we pick this as a vertex cover example. This is covering these edges, A, C, E, and D, right? Now, by adding these nodes in between, I am forcing this problem to have to cover these new nodes, which then corresponds back here to having to cover these edges. Now, this is very fuzzy because we've just trying to justify Jeff's intuition. And it's not clear to me that this even works. How do we check that it works? We have to show that any vertex cover of size 5 for here can be converted to a dominating set of size 5 here, and vice versa. Any dominating set of size 5 here can be converted to a vertex cover of size 5 here. That if you can solve this, then you can solve that, and if you can solve this problem, then you can solve this problem. This is the best way to do reductions for beginners. Try something like this. Chuck in your intuition, even if you're not sure, and check whether it works. If it's a little bit broken, we can fix it. And if it's a lot broken, come up with a better intuition. So let's check whether it works. To check whether it works, we're going to go back here and ask ourselves, if somebody gives me a vertex cover of size 5 here, how will I show you that there's a dominating set of size 5 here? Well, maybe we should actually show a vertex cover of size 5, and it'll be easier. Anybody come up with one?
B, C, E, F, H.
B, C, E, F, and H. Let's just double check. Looks good to me. I'd like to convince you that if you have a vertex cover of size 5 here, then you have a dominating set of size 5 in Jeff's graph. Why do I? I'll just use the same nodes. That'll be my try. B, C, E, F, H. Does it cover all the nodes here? Did it work? Am I lucky? Almost. It certainly covered all these new nodes that we put in, right? But it didn't cover this one that got stranded, and it didn't cover that one that got stranded. Crap! What a good idea that didn't work. And in fact, it just seems like we made it harder to get the cover. Let's take these nodes out. Goodbye, Jeff's idea. Would it give me a dominating set then if I took those nodes out?
You wouldn't need that many.
Yeah, you wouldn't even need that many, but can I do it with 5? Yeah. Certainly. I mean, any vertex cover can just be copied over to the same graph, and it's definitely a dominating set, right? Because if you're covering all the edges, you're certainly covering all the nodes. So I'm getting rid of your thing, Jeff, because now that first part works just fine. I'm going back to don't change the graph at all. Remember I said it wouldn't work, but nobody asked me to check. Now we're going to go back to let's not do anything and let's check. the vertex cover here, if you don't do anything, ends up being a dominating set here. But now let's go the other way. Say we have a dominating set on this graph. Okay, it's not changed now. Is it going to be a vertex cover here? Not necessarily. So that's the tough part. And that's why Jeff put his little things in. If these things were in here, and I have a dominating set of size 5, if these nodes are in here, and I have a dominating set of size 5, then what do I know about that same set over here for vertex cover?
You can't necessarily do that because those nodes disappear then if those nodes are part of your dominating set.
But if these nodes are covered, it means that the edges that the nodes were put on are covered.
Right, but I mean, you can have a dominating set of size 5 using these extra nodes we've added, in which case...
We'll deal with that objection in just a minute. But let's get the first part. It's a good objection. If I throw in Jeff's nodes, and I have a dominating set on this graph that use some collection of these letters A through H, then I could just bring it back and know that it's a vertex cover, because if these nodes are here, that means I have to cover these nodes. And if I cover these nodes, it means the edges that they were on have to be covered. So Jeff's idea is great for going back. But when we went forward, it didn't work. We put too much in. Now our vertex cover doesn't correspond to the dominating set because we left this stranded. But it's a really good idea, and it's almost there. So can we fix Jeff's idea, and then we'll deal with some of the details that I'm fluffing over that Chris just mentioned. Can we fix Jeff's idea so it works forward and not just backward? It's a good idea. This is a good idea to force a dominating set here to correspond to a vertex cover here. But then the vertex cover didn't correspond to a dominating set because here, we covered this edge. But now when I cover this guy, although I cover this edge because I'm covering this, I can't cover this guy anymore.
Can you only put
Exam notes just put in the marked guys.
Say that again?
So you copied the graph over
Yeah.
marked nodes, and you put in the new nodes only between the marked nodes.
Oh, great idea. And I'm being sarcastic. It's a great idea, but this is like a classically good example, and I'm really glad you came up with this idea. Sham wants to do a particular thing in the reduction that's based on where I put these x's. Right. You'd have to figure out where the vertex covers first. But this is very common, and you can get this in a lot of subtle ways. It's very easy to start making your reduction depend on the actual finding of a solution. Don't confuse that with what I did a few minutes ago, which is if you have a solution, I want to convince you there's a solution there. The reduction must be done before that argument. You cannot make your reduction based on where the solution ends up being. Otherwise, you have to actually solve it to do the reduction. And that's going to take exponential time.
What if we removed all of the additional nodes that we added that connect to a node that only has 2 edges coming out of it, or something like that? In this case, the uppermost triangle and the lowermost triangle both have nodes that are only connected to 2 others.
Yeah, I'm not sure that's going to work in general, though I'd have to check it. But I kind of doubt it's going to work in general.
D also will miss, that doesn't fit the criteria.
Right, we'd still miss this guy. Here's a way. You're going to be annoyed at the simplicity of this way. Do just what Jeff said, but don't get rid of the edge that you used to have here. Jeff said put a node in between. But leave the old edges in. Just add an extra length 2 path between every 2 nodes that used to have an edge. Don't get rid of the old edges. Then your idea is going to work. Let's see why. We're going to go forward again. If there's a vertex cover on this graph, I'm going to use the same nodes on this graph to cover this with a dominating set. How come? Well, the vertex cover covers all the edges here. If it covers all the edges, that means every one of these new nodes I put in has to get covered because one side of that edge is going to be covered. All the edges that used to be on the graph are covered, so all the nodes connected to them are covered. So all these nodes get covered. So if I have a vertex cover, I will have a dominating set. Now let's go backwards. If I have a dominating set on this graph, and let's say we're lucky and it corresponds to nodes that actually appear here, that the dominating set is not any of these new nodes. This dominating set covers all the nodes on this graph, including all the new nodes. As long as it covers all the new nodes, it has to cover either from this side or from this side. That means it covers the edge at which those new nodes were added. So everything works perfectly except for one little subtle point that Chris mentioned a minute ago. What if my dominating set on this graph doesn't use the nodes that correspond to A, B, C, D through H? What if they actually use these new nodes?
Can we make those uncoverable somehow?
Yes, we can. How do we make these uncoverable somehow? By pointing out that only an idiot would actually try to cover this graph by using one of these nodes. Why? What do you get by covering this? What do you get?
You cover two nodes.
You cover these two. I could move this guy to either side and cover everything this guy does and more. So here's what I say. You got a dominating set for this graph that takes a certain number of nodes. If any of them use the middle, pat yourself on the head like that and move it over to one of the edges. Then I'll show you the corresponding vertex cover. Doesn't matter what you do. I can take your solution, make it better, and then convert it back. Okay? Therefore, summarizing. There is a reduction from vertex cover to dominating set. The reduction says for every edge in this graph, add something like this. And then a long argument explaining why a solution to this corresponds to a solution to that, and a solution to this one corresponds to a solution to that one. These problems are very similar to one another, and now you see why. They really are the same problem with an edge corresponding to a vertex sitting in the middle of that edge. Really the same kind of thing. It might be scary, but the reductions between problems that are not this similar can be much, much more hairy to see the connection, even when somebody spells it out. Right. So we've been here a while, and you're all thinking, oh, Jesus, now he's going to go do this one. I'm not going to do this one today because it's late, but I'm going to do something instead that's a little easier. Okay? I'll leave this for tomorrow. I'll leave this for tomorrow. You know what I mean. Monday. And instead, I'll concentrate on something which is a different kind of way of thinking, and you can relax your minds a bit. Relax. Let's go back to vertex cover. Since you've been thinking of that and your mind's all with it, you don't have to think of something completely new. You know the problem vertex cover. What if you really wanted to solve this problem, now that you know that it's NP complete? You really have to figure out a way to do it. Give me some instincts. How would you try to solve this problem? Well, the best way we can do it will be exponential. But what would you try to do if you had to do it? Minimum vertex cover for this. What's your gut instinct? What's your first guess at a method?
A greedy strategy.
A greedy strategy. Good. Now, no greedy strategy is going to work, but maybe we can come up with a greedy strategy that'll get close. What I'm going to try to convince you, and then we'll finish today, is that there is a greedy strategy that will solve the vertex cover problem, and if the minimum is, say, 3, then it'll get no worse than 6. The worst it'll ever get is double the actual minimum. So if you don't mind being 100% off, we got an algorithm for you. That kind of algorithm is an approximation algorithm. Some approximation algorithms are only 25% off, guaranteed. So even though the problem is exponential, you can do it real fast if you don't mind being a little bit off. Approximation algorithms are super ways of dealing with NP-complete problems. There's other ways. Consider restricted cases that are no longer NP-complete. That's the most obvious kind of thing. There are other ways. Do a randomized algorithm. Mark was telling me that his advisor or colleague at the University of has a randomized algorithm for 3-sat, for satisfiability, for 3-sat. And a randomized algorithm means that it's flipping a coin to decide what to do next. So the analysis of it is going to be quite tricky. But it will always get the right answer with this flipping of a coin strategy in 1 point, what is it, 1 point? Exponential, but that's the expected running time. Now, that's not so bad in practice. You can get pretty big n's in there before it starts to blow up. So you can solve that problem using this very tricky randomized strategy. There's also probabilistic algorithms, algorithms that are not guaranteed to give you the right answer except 98% of the time. They'll run fast, but 2% of the time their answer is completely untrustworthy. So it depends. It depends if you just want kind of a ballpark figure for something and you don't mind being wrong, or if you're sending 3 people out in the space shuttle.
Do people commonly combine two? One like use a probabilistic and use a approximation at the same time, and if they differ by 25%, then they know that one of them's bad and they can.
That's a clever idea. I don't know. I'm not sure. I can check. Usually the things that I've seen are just papers that publish one or the other, and I haven't really seen a discussion of let's attack this and bring everything to bear.
Especially a parallel process, and you could just run them both parallel.
Right. Well, you certainly do that with probabilistic algorithms in order to minimize the chance of it being wrong. I'm not sure. It's a good question. Okay, so let's get back to vertex cover and actually do an approximation algorithm today. So, greedy strategy. What kind of greedy strategy?
Pick the vertex with the most edges first. Cover it.
Okay.
See what's left to cover.
Everyone understand Chris's idea? What do you think of Chris's idea? Is that what you would do? Donna, you would do it? You like it? You like Chris's idea? Gary, you like Chris's idea? Thumbs up. Everybody's thumbing up. Nobody's thumbing Chris's idea down? All right. So this covers all these edges. Why? Because he wants to be greedy. He wants to cover as many edges as he can in the first guess. What would get covered next? I guess anyone with a degree 3. So this one, or this one. So we'll cover this one next. And now we'll cover this one next. And now we'll cover this one.
No, we've already got that one.
No, because we don't have this edge. So Chris is kind of implying in this algorithm that he's not just going to take them in order of degree, but if he actually gets to one, all of whose edges are covered, he's going to skip it. Good idea. But we didn't have that here, so we're...
You
can
take away
decrement
the
the
edges
edges
that you've already
when you-
covered from the calculation.
Oh, there's a different idea. Okay, so you're thinking about that. All right. Well, now you are. There's a good idea. Start with the biggest one, take those edges away symbolically, and then recompute the degree, and then continue that way. Good. Interesting. Do we have any idea whether this is going to give us some kind of a bound? We don't. Can we analyze it? We could. Do we have enough time to? We don't. I can tell you one thing for certain, is that Chris's original idea, without redoing the degrees, just by going in order, it wouldn't take you too long to come up with an example where it just does horribly, where it basically gives you every single node in the graph, even though you could get like 3. Right? So the first instinct is actually a bad instinct, and the secondary instinct to fix it, or which might even be the same instinct, we don't know about. But I would challenge you to think about that second, seemingly better way and see if you could show me a counterexample, an example where it gives a horrible answer relative to the real answer. What I am going to show you is a method that is talked about in the book, a method that does get an answer at most twice as bad as the right answer. And it has nothing to do with the degree. It's a different method. But the argument is going to be straightforward. It's not going to be one of these convoluted, what the heck's going on kind of algorithm. So let's do this, and then we'll quit today. Okay, here it is. Here's how this algorithm more or less works. Go in your graph and pick any edge at random. What do you want to pick? Okay, we're picking the top one. Now what?
See if you're done.
See if you're done.
Confirm yes.
all these edges connected here are covered up, right? We don't need to cover any of those again.
Assuming we've picked the two vertices.
Assuming we pick both of these, right? Right. So what do we do next? Where should our next?
Just randomly pick another edge.
Let's pick another edge that isn't connected to these. Anyone. How about this one? Okay. And now again, let's pick another random edge that isn't connected to any of the nodes that we have. Let's keep doing it until we can't do it anymore. I think we're done, right? Any edge we pick now is going to be connected to one of the other edges that we have. I basically picked an independent set of edges. Not the minimum independent set, any independent set of edges. You can certainly do this in polynomial time. Just look for any independent set of edges you can get. Well, what good is this for a vertex cover? If I took both ends of these edges in the vertex cover, it definitely covers all the edges. Right? Because if I add another edge in, it connects to one end of one of these. So I get a vertex cover here of size 6. Can you convince me that the actual vertex cover here has to be at least 3? Everyone understand what I want you to convince me of? If you could do that, then I know that this is no more than twice as bad as the best. How do I know, staring at this picture, that I need at least 3 nodes to cover the edges here?
Because you need at least one for each of the segments.
Good. You see these hatched edges? They all have to get covered in the vertex cover, right? That means there's got to be at least one end of each one that's got to get covered. Right? I can't possibly cover all the edges and have all of these missing. So I got to have at least 3 in my vertex cover. It's possible that if I picked exactly 3, it would cover all the other edges too. And in fact, does it? I think I might need 4. But it's possible that I could get it all with 3. But I need at least 3 because the hatched edges that I just scribbled on have to get covered. And if they have to get covered, then either one end or the other has to be covered. And they're all independent. They don't share any nodes. So I need at least 3 to cover this graph. Or putting it this way, any independent set of edges on your graph is a lower bound for the vertex cover. You got to have at least that many nodes in your vertex cover. If you can find 3 independent edges in your vertex cover, you got to have at least 3 nodes in your vertex cover. If you could find 4 independent edges in your vertex cover, you got to have at least 4 nodes in your vertex cover. This is a lower bound, a minimum. But when I actually do this algorithm, I get a vertex cover of size double that. So my little greedy strategy is getting at worst twice what I could do in the best case. This is very clever. It's a really neat idea. And it gets us down from I can't do this problem at all to I can do it as long as you don't mind me being twice off. Okay. The questions about this idea? It's not complicated. It takes a little bit of thought to realize that it works true. And it's very different than this degree idea that we first tried, where we had no way to make a handle on showing it was related to the minimum at all. Here, we really can. Questions about this?